Okay, so I just want to start with a recall from last lecture, the main points that we will need today. So mainly I want to discuss the simplex algorithm and its implementation. Okay, and I mean there are two views to it. You can think of this as like algebra and math, or you can think of a geometric view, more intuitive. Okay, and I like the second. So strange. Okay, something wrong. Seriously? Okay. So we will first talk about simplex and its implementation. Then we'll briefly talk about, so simplex requires first computing a starting vertex, which is again equivalent to solving LP. So are we going in circles here in a recursion? Then we'll talk about some problems that the simplex has to handle, like infeasibility, unboundedness, degeneracy, and finally, if you have time, we'll talk about duality. Okay, so let's start with what was the problem. So we had a matrix A, which had n rows and d columns. The rows correspond to constraints, and columns correspond to variables. And a right-hand side vector and a cost vector. Okay, cost. And we want to solve this problem. Now, the first thing we want to, so because we want to maximize the linear function over these constraints, first we should understand what the feasible points are. Okay, so we said that the feasible set of points form a convex set. What do we mean by a convex set? This is a convex set. Okay, if they just connect properly. That means if you take any 2 points inside the set, the line joining them is also inside the set. Okay, so is this a convex set? No, right? Because if I take these 2 points, then the entire line is not in the set. Is this the convex set? Right, this is, right? So we formally proved that this set of constraints form a convex set. Okay, and it is actually this type of convex set, not this type. It's not smooth boundary, but it's like it has corners. Okay, why is that? Because when you look at any constraint in the set of n constraints, it forms a hyperplane. Okay, so the constraint equality would form a hyperplane, and when you look at the inequality less than or equals, that forms a half space. So what do we mean by that? So suppose you are in 2 dimension, and I say x1 greater than or equals 0, this constraint. What half space does it form? It is all these points, right? Right? Now if I say x2 greater than or equals 0, that is all these points. Right? And then if I say x1 plus x2 say less than or equals 1, then where should it intersect with x1 axis? So suppose I say, look at first the equality. So look at, so this has to form a line, right? This forms a line in 2 dimension, the equality, right? Where should this line intersect x1 axis? What do we mean by x1 axis when x2 is 0, right? So on this axis, x2 is 0 because this is a 0, 0 point. So if you look at 1, 0 point and here a 0, 1 point. So this line is passing through these 2 points. And when we say less than or equals, then this segment is feasible, this segment is feasible, all of this is feasible. So this intersection of the 3 forms the convex set through these 3 constraints. Okay, and in a higher dimension, it will be just more complicated. So it will be like if you try to imagine in 3 dimension, let's say this is x1, then x1, say less than or equals 1 would form some hyperplane which intersects x1 at point 1 here. So 1, 0, 0. Okay, so there will be some kind of hyperplane passing through this point. Okay, and all the points on this side of the hyperplane are the feasible point. So that's why when we talk about these constraints, it forms this nice polytope whose boundaries are linear, and then they intersect at corner points or lines or whatever. Okay, if 2 hyperplanes intersect, it forms a line, right? So they will form a line here. So this is a bit about the geometry of the polyhedron. Now, we said that if you want to, so another point is that if we are taking, so another view of a polytope is just that so you have these corner vertices and you take convex combination of this all possible convex combination of these corner vertices. Okay, so suppose I have x1, x2, x3, x4, x5, then if I look at any x which is lambda 1 x1 plus lambda 2 x2, lambda 3 x3, where all lambda I are greater than or equals 0 and summation lambda I equals 1, this is called convex combination. Okay, so that is another view. And if you take a convex combination of a set of points, so suppose I say A is a convex combination of some set of points AI, then I know that the maximum and minimum value is bounded by the max and min of AIs. Right? So that's why when we try to optimize a linear function over a polyhedron, a vertex has to be a solution, exactly because of these 2 reasons. That the polytope is actually convex combination of its corner points, and if you are maximizing, say, some C dot x, then it cannot be possible that this point, interior point, is a solution, but none of the corner points are solutions. Because you can write C dot x as summation I lambda I C dot xi, right? And then you get that by the same reasoning that C dot x has to be at most max I C dot xi. The cost vector we had in the linear program. So we are trying to maximize a linear function over a polyhedron. And I'm trying to argue that it cannot be possible that there is no vertex solution of this. There has to be a vertex which is the optimal solution of this program. Because if there is an interior point which is a solution, then that interior point can be written as convex combination of all the vertices. Okay, and then if you look at C dot x value, your objective, that is just the convex combination of C dot xi's. That is objective value at corner points. Okay. So this value cannot be the max at the corner point. Okay. So now this vertices of the polyhedron are also called basic feasible solution. This is how the problem in the homework is defined, right? It's about basic feasible solution. So basic feasible solution is just a feasible vertex. Formally, it's a feasible point where the linearly independent constraints are tight. Okay, and we will just say that the constraint I is tight if this inequality holds with equality. We'll just say hyperplanar constraint is tight. Okay. Okay, any questions? Okay, so what we have seen is that we have set of linear constraints, each defines half space. If you take the intersection of that, we get a polyhedron. And we know that the optimal value of the LP is at a vertex. So what simplex does is it pivots from vertex to vertex. So it starts from some feasible vertex, moves to its neighbor, moves to another neighbor, and so on. Okay? Now the question is which neighbor to move to, when to stop, and how much time does it take, the entire thing. Okay, so we'll try to answer these questions and then the algorithm will be clear. Okay, so suppose we are at a vertex x hat and it is not optimal. Okay, then we know that there exists some optimal vertex. Let's call it x star. Okay, so we know that the objective value at x star is more than the objective value at x hat. Okay, so now I ask, what happens to this objective value as we move from x hat to x star in that line joining the 2 points? So the claim is it strictly increases. Why? Because it's a linear function. So let's say d is the direction of movement from x hat to x star. Okay, so d is x star minus x hat. Now you multiply c dot d. It is just c dot x star minus c dot x hat, but that is strictly greater than 0 because of this property. And when you are moving from x hat to x star, you are essentially moving in direction d from x hat. Right? So if you look at all the points which are x hat plus delta times d, where delta goes from 0 to 1, so if delta is 0, then you are at x hat. When delta is 1, then you replace d here, which is x star minus x hat, you get x star. Sorry. Right? So as delta goes from 0 to 1, you move from x hat to x star. And if you look at c dot x, it is exactly c dot x hat plus delta times c dot d. But this is positive, this is positive. So as delta increases, the quantity increases. So the point is, if you are at a vertex which is not optimum, then there is a direction of movement from that vertex so that the objective value improves. Okay, so I am giving you kind of constructing this direction. But the problem is I don't know x star, so how do I construct this direction? And that's the whole point. Okay? So we'll have to go to cones to understand this. So a cone of a set of vectors is just positive linear combination of those vectors. So summation lambda I di, where lambda I is non-negative. That's a cone. So in 2 dimension, if I have these 2 vectors d1 and d2, then the portion inside between these 2 is a cone of d1 and d2. Okay, if you try and see, then if you kind of try to put all these vectors here, you will see that it will be exactly these points.
Can lambda be very large?
Yeah. So that's why there is no end. You can go to infinity. But it has to be between so you make this line go to infinity, this line go to infinity, and all the points in between will be. So it's not a convex combination, but it's just a positive linear combination. Yeah.
Is there a number of lines that we need for some particular amount of dimensions? We have 2 dimensions there, and we have 2 lines to form a cone.
Good point. So in 2 dimension, so if there was a third, say, vector here, d3, that didn't mean anything because that is just a combination of, so then your space will be this, which says that just D2 is inside the cone of D1 and D3. So D2 is useless in that sense to define the cone. But is that true for 3 dimension? Can you define a cone uniquely by 3 vectors? Pyramid. Think of pyramids. So there is this top vertex, right, in the pyramid. How many sides come together at that vertex? 4 of them. And that has those 4 edges that they make, right? So this is kind of a pyramid I have made here, as inverted pyramid, right? So it is true in 2 dimension but not true in 4 dimension. To make this cone, which is needed for pyramid, whose base is a square, you need these 4 directions. Now imagine a cone, a smooth cone, like an ice cream cone. Okay? If you discretize it, like you put it a lot of facets, right? Make it a linear, but by putting a lot of facets, then you will see that there will be so many lines forming that cone, right? So all of those lines are necessary to form that cone. So true in 2 dimension, not true in higher dimension, more than 2.
What if, like in the three-dimensional case, what if there is a vector inside of this cone?
That's a useless vector to define this cone, right? Because
Then it's not unique.
it's not unique, no. I'm not saying it's unique, but it's like you can forget. So suppose there is a D5 which is going inside, like this vertical line, then you can as well just remove D5 from the definition of the cone, right? Because it's not adding anything. If you remove that, you are not shrinking the cone. Yeah.
So there's no finite value for which in 3 dimensions we can uniquely define each cone?
No. Okay. So music. That must be a fun class. Okay. So now I want to think of, I'm standing at a vertex. I look at all the edges going out of this vertex. Think of those forming a cone. Okay, all the edges. So I am at a vertex, say I am at this corner. Okay. There is this edge here, this edge here, and this edge here. All 3 are forming a cone. Now, if I want to move in any of these directions, it is inside this cone of these 3 edges. Right? So if you are at a vertex, okay, and if you look at the cone spanned by the 3 edges to its 3 neighbors, or whatever, D edges to its D neighbors, then any feasible movement from that vertex, the direction, is inside that cone. So this is very nice, right? Because, okay, we don't know what x star is, but we know that movement from x, so if you want to move from x hat to x star, that direction is in the cone of this D1, D2, D3. Now we will use this, the fact that the cone is made up of positive linear combination. So now I claim that, suppose D is inside the cone of these vectors, then if C dot D is greater than 0, then there exists a DI such that C dot DI is greater than 0. So this is perfect, right? So let's say first why this is true. So suppose to the contrary, there is no I, for all I, C dot DI is less than or equals 0. Okay? Then when you, and D we know is a positive linear combination of DI because D is inside the cone of D1 through DK. So when you look at C dot D, that is exactly C dot this positive linear combination, which is exactly by linearity of dot products, linear combination, positive linear combination of C dot Di's. But if all of these are at most 0, how can this quantity can more than 0? Simple, right? So that's a contradiction. So this is saying that if at a vertex there is a direction of improvement, okay, then there is a direction of improvement to one of its neighbors. And those are finitely many, right? Probably those are practical enough to check, kind of. Okay, so this is just saying that if x hat is not optimal, then it has a neighbor where the cost improves. Question? Okay, so this is good. We can go to one of the neighbors, but how many neighbors can there be of a vertex? Two, three. So let's see. It depends on. It should. So how many vertices? How many neighbors are there of this vertex where I am standing? 1, 2, 3. Right? But if you are in 2 dimension and you are looking at a polygon, then how many neighbors can there be of any vertex? 2. So it depends on dimension. It's not simple answer, right? Yeah. So vertices are actually 0-dimensional phase. So there is no, you cannot move from a vertex anywhere and you still remain on the vertex, right? Edges are 1-dimensional phase and hyperplanes are d minus 1-dimensional phase. So these dimensions are like how much freedom of movement you have, okay? And in general, R linearly independent tight hyperplanes form d minus r dimensional phase. Okay, you can try and think about this. I don't want to formally prove this. Okay. So vertices being 0 dimension, we will need d linearly independent hyperplane to meet. So in 2 dimension, if this is a vertex, then we need 2 linearly independent lines to meet. Right? They cannot be linearly dependent, like this line and this line, which is x1 equals 200 and x1 equals 0. They will never meet because they are parallel. Right? So to form a vertex in 2 dimension, you need 2 linearly independent constraints or hyperplanes to meet. In 3 dimension, there are 3. Okay? So in 3 dimension, 3 linearly independent hyperplanes or constraints, when they hold with, they are tight, you form a vertex, and 2 of them forms an edge. Right? So if you have like it's a plane, you intersect it with another plane. What do you get in the intersection? Line, right? And you intersect it with third plane. Then what do you get? The intersection of all 3. A vertex, right? So in general, in d dimension, you have d hyperplanes, linearly independent hyperplanes tied at a vertex. Okay, and on an edge, d minus 1 will be tight. Okay. So when we want to move from, say, x hat to x prime, what are we doing? On this edge, two hyperplanes are tight, and these two hyperplanes are tight at x hat as well as x prime. But there is an extra hyperplane tight at x hat, and when we leave that, so 3 is an hyperplane which is tight here but not on this edge, entire edge. Right? 3 is tight at x hat but not on this edge. So when you leave 3, when you relax 3, we will see what do we mean by that. We move away from x hat and towards x prime. And there a new hyperplane will become tight. Okay, so between neighbors, they share d minus 1 tight hyperplanes, and they differ by exactly one tight hyperplane. And this will tell us how to move from one vertex to the neighbor, to its neighbor. Okay, so for every tight hyperplane at a vertex, when we leave it, we go to a neighbor. So suppose I leave 3, I know that I go to x prime. If I leave 2, where do I go? From x hat. So from x hat, suppose I relax hyperplane 2, where do I go? Down, right? I'll go here. Right? If I leave 1, where do I go? Here, right? So when I'm moving from a vertex, I have to relax exactly one hyperplane while keeping all d minus 1 hyperplane tight. That's the thumb rule. Okay? Sorry? The hyperplane, so tight meaning it holds with, the constraint hold with equality. Okay, so you see, as I leave I relax different hyperplanes, I go to different neighbors. So essentially, you will have, if d hyperplanes are tight at a vertex, then you have d neighbors, typically. There are exceptions, and we'll see what happens with the exceptions. Okay? So the vertex has d neighbors, so not too bad, right? We can check in every step, we can check if any of the d neighbors have better objective value than the current vertex. If yes, then we can move to one of the better ones, and we can continue, right? So we got the answers to our 3 questions. Which neighborhood to move? Move to the one where objective value increases, right? When to stop? When there is no neighbor with a better objective value than the current vertex, right? Because we proved that if there is a vertex with a better objective value, there has to be a neighbor with a better objective value. So if there is no neighbor with a better objective value, that means this vertex is optimal. Is this point clear? Okay, and third, how much time does it take? So I can say that in every step, I just have to check d neighbors. So probably order d or d square or whatever, around that. Every step is order d or d square. Overall, we'll see how much time it could take in worst case. Okay, so the simplex is, you can imagine, right? You start, what would you do if you have all these answers? You start at arbitrary vertex. If it has a neighbor with a better objective, you move to that. And again, you do the same, repeat the same step. If there is no neighbor with a better objective, you stop. That's simplex. It's as simple as that. So when Danzig, I very recently came to know, when Danzig, he invented this in I think 1946 or something, or 45 or 44 at some point, and at that time von Neumann and many other people were trying to solve linear programming with different methods. And he thought that this is such a stupid method, right? Moving vertex to vertex, I may kind of traverse all the vertices, and there can be exponentially many vertices in a polytope. So he never implemented it. Okay, never he thought it's a stupid algorithm. Then people were trying, and no method was good. Every method took a lot of time. Okay, so then he came back to this and implemented it somehow. I don't know why. I mean, I think he got another view of it, and that's why it's called simplex. And so he implemented that, and it turned out to be super fast. It beats all it. At that time, it beat all the known algorithms, and still it beats, for many of the problems, all currently known algorithms. Okay. So in practice, it's a super fast method to solve a linear program. It feels like you are just doing local optimization, moving to a improving neighbor, and that's it. But it just works really good. And we kind of know now why it works good. Okay. There is a whole concept of smooth analysis developed to just understand this, actually, this phenomenon. Okay, so simplex is a greedy local improvement algorithm. Works because local optimum is global optimum. So basically, when you have a vertex where there is no improving neighbor, then you can stop. So let's see, how do we implement this pivoting step? How do we go from one vertex to another vertex mathematically? Suppose you want to code this algorithm. How would you do that? Okay, so we know that if we are at a vertex, at the neighbor, when you move to that neighbor in that direction, d minus 1 hyperplanes will remain tight, and exactly 1 will be relaxed, right? So now let's look at all the tight hyperplanes at a vertex. There are d of them. Okay, so let's say that it forms this system A hat x equals B hat, where A hat is D cross D matrix. Okay, and B hat is D cross 1 vector. So you took the D inequalities which hold with equality at this vertex and set up this linear system. Now look at minus of A hat inverse. I claim that the D columns you get for this matrix are exactly the D direction of movement for the D neighbors. Okay, so if you look at the ith column of this matrix, let's call it di. Then I claim that from x hat, if you move in this di direction, then you keep all constraints tight except ith constraint in this system A hat x equals B hat. That means that except I, all other hyperplanes remain tight when I move from x hat in this direction di. Okay, so why is that? Because let's say y is x hat plus epsilon di, that is just exactly saying that you are moving in the di direction from x hat. Now if you look at A hat y, that is exactly A hat x hat plus epsilon times A hat, and then di is the ith column here. So let me just write it as minus this matrix and ith column of that. That's what I mean by that. But when I multiply a matrix and its inverse, what do I get? Identity matrix, right? And what is the ith column of this identity matrix? You just have zeros and 1 at the ith coordinate and zeros, right? It's ith unit vector, right? So this quantity is exactly just zeros minus 1 at the ith coordinate and 0. And so you are just subtracting something from the ith coordinate of B, and the rest of the coordinates remain the same. So you're keeping all the constraints which are not I to be tight and relaxing just the ith constraint. Relaxing, why relaxing? Because Bi minus epsilon will be strictly less than Bi. Yeah.
Can you say why is the magnitude inverse of n at
I'm just saying that let's take this matrix and call its columns D1, D2 to DD. I'm just naming its columns. And now I'm claiming that the dith column of this matrix is exactly the direction of movement when I relax ith hyperplane at this vertex. Right? And this is what I needed, right, to move to a vertex, to see all the vertices. So these are all the directions of movement for all the neighboring vertices of X hat. Okay. So now, I know that when I'm moving in di direction, I am keeping all the k naught equals I constraints tight out of the first d constraint. Ith constraint is getting relaxed. But what about the other constraint? There were n constraints, right? Out of that, we took just d of them in a hat, right? So when you move, no other constraint should become violated. Like in this case, when you move from x hat to x prime, you know that 3 is getting relaxed. So you are moving in a right side of 3. 1 and 2 are still tight, but we have to make sure that we don't go so far that 4 or any of the back ones get violated. Right? That tells us how much can you move, the epsilon value. So that's exactly we do. So let's say you take a constraint k which was not tight at that vertex, and let's say we denote ak be the row of the coefficients of that constraint, okay, kth row of A. Then if I look at this quantity which is AK dot product with the point that we are trying to compute, so think of epsilon as a variable here. It should be less than or equals bk. If you simplify the entire thing, you get that epsilon should be at most bk minus ak times x hat divided by ak times di. Okay, it's just algebra. And I can do this division here, so I get epsilon times ak times di less than or equals this quantity. Now I can divide this only if this value is greater than 0, otherwise I swap the inequality, right? So now, is this quantity positive or negative? So is the numerator positive or negative? Remember that x hat was a feasible point. So we knew that ak x hat was less than or equals bk. Right? So this is a positive quantity. So we get an upper bound on epsilon which is a positive upper bound. Okay? If this was negative, then we get a lower bound which is a negative lower bound, so that doesn't mean anything. So basically what is happening is when two vectors, the dot product of two vectors are positive, when does it happen? When they are in the same direction. The angle between them is less than 90 degree. Right? It is negative when the angle between them is more than 90 degree. So essentially this is saying that if you are moving towards some hyperplane, then you get an upper bound on epsilon. If you are moving away from hyperplane, then there is no upper bound needed, right? Because you are kind of going inside the feasible region from that hyperplane, for that half space for that hyperplane. Right? So you don't need any bound on epsilon for that particular hyperplane, to make sure that that particular hyperplane remains feasible. So suppose this is the hyperplane, okay, and this is the feasible region, okay, and I want to make sure that this never violates when I'm walking towards this. So I always remain this side of the hyperplane. Is there any bound up to which I can walk to keep this feasible? No, right? I can keep walking up to infinity. And this will always remain feasible because I'm moving opposite to the hyperplane. Okay, so for those which are moving away from the hyperplane, you don't need to take care of that, because that just gives you a lower bound which is negative. And when you are moving towards hyperplane, you get an upper bound, and you have to pick the one which is you get a set of upper bounds, pick the minimum one, right? So that gives you an algorithm. So you set epsilon to infinity. Then for all the hyperplanes that were not tight at this vertex, compute the possible bound. That bound has to be positive, and if it is less than the current epsilon, you reset the epsilon to that value. Basically, you are just computing the minimum value, minimum positive upper bound. Okay, and then this will return you the vertex. So finally return the vertex. So it's basically just x hat plus epsilon times di. And this vertex will be an improving vertex if c dot di is strictly greater than 0. Right? At this vertex, if c dot di is strictly greater than 0, then c dot x hat plus epsilon di, which will be c dot x hat plus epsilon c dot di, which will be strictly greater than, right, c dot x hat. Questions? Yeah.
What does epsilon less than, the last two line?
You're saying what if epsilon is negative?
Epsilon less than.
Infinity. The last second line, epsilon smaller than infinity.
So good point. When will epsilon be infinity? Can it? So I initially, like, what do I mean by infinity? I cannot initialize any value by infinity in a computer program, right? Basically, you set it to some value, you know that epsilon will be always smaller than that. Okay, so a huge value. Say huge to the huge something. Okay. Now, suppose you run this algorithm, and at the end, at this point, so when you complete this for loop, here epsilon is still the same value, huge to the huge. What does that mean? You never got an epsilon prime which is larger than 0. Right? What does that mean? Kind of. But when you are trying to move from this vertex by relaxing a hyperplane, you are moving away from all the hyperplanes. Right? That's when you had a negative epsilon prime. You had a negative epsilon prime when you are moving away from that particular hyperplane. When you are moving away from AK. This is a very good point, actually. Very important point. Okay? What does that mean? When can it happen? Suppose this is my polytope. Okay? That side, this side, above, below. Okay? But there is no this wall. This wall is not there and nothing is there up to infinity. Okay? And suppose I start moving from here on this direction. Where will I go? I am moving away from all the hyperplanes, right? I cannot go there because I am in parallel to that. Moving away from there, right? Where can I go possibly? That's the situation where you will be if this happens. Basically, you are in an unbounded polyhedron. Okay? In this direction, there is no stopping. Okay? And it may happen. Yeah?
Can you explain why we only check the rows from t plus 1 to n instead of all of them?
Good point. Why? Tell me. I mean, any answer. Wrong, right, anything. Any intuition. What was happening when we were moving on an edge? So there were 3 hyperplanes tied here at this vertex. Those are my first D hyperplanes, right? When I move from x hat to x prime, I know that I'm going away from 3, so I don't need to check that. I know for sure. And I also know that I'm not going to leave 1 and 2. 1 and 2 will all still remain tight. So I know what is happening with first D. And that's what we prove in this lemma, that if you take the inverse of A hat and multiply -1 with it and call its columns D1 through DD, now if you take the ith column and start moving in that direction, then you move away from ith hyperplane, you keep all but the ith hyperplane tight out of first D. Okay, so you know what is happening with first D hyperplanes. So that's why you just need to check D plus 1 through n. And these indices, you are right, as you change the vertex, these indices will change. So it should be all the hyperplanes which are not tight at x hat. That should be the index here.
Okay. So you start with constraints from 1 to d, and you're trying to find another one that's...
Yeah, so I am assuming that the first D constraints are tight at x hat. So here, in general, it should be, so this should be k such that kth constraint is not tight at x hat. So for all k you have to do. Okay. Okay. So let's just see this entire thing through an example. What does this A inverse mean, and so on. So let's say this is our polytope, our example, and so these are the constraints. And let's say I look at the 0, 0 point. That's a feasible point in this constraints, right? So that's this vertex here. What are the constraints that are tight here at 0, 0? Can you say the constraint explicitly?
0 is equal to the, or 0 is less than or equal to x1, 0 is less than or equal to x2.
Yeah. So, good, thank you. So these two constraints are tight there, right? 0 at 0, 0. So in our format, we write it as minus x1 less than or equals 0 and minus x2 less than or equals 0, right? So when I write A hat, that's just -1, 0, 0, -1. So the minus of A inverse is just identity matrix, right? And these two columns, this is D1 and this is D2. Okay, so now if I move in D1 direction, where do I go? So this is D1, 1, 0. This is D2. I go here, right? This is the D1 direction. From here, I go towards increasing x1. Right? So I hit 200, 0. If I move in this direction, then I am increasing second coordinate, so I'll be hitting 0, 300. Right? So in D1 direction, I left this, but I gained this hyperplane. And in D2 direction, I relaxed this, but I gained this one. Okay, I'm taking a very simple example, but just to illustrate. Okay, now, so suppose I take this direction. So both of them are improving direction, right? Because at 0, 0, the objective value is 0, 0. What is the objective value at 200, 0? 200, right? What is objective at 0, 300? 1800. So suppose I take a better one. At both places it improves, so I take a better one. Now where should I go so that it could improve? And that will be this direction here. So this is the optimum point. Instead, so this is like just 2 pivots, right? Instead, if I took, or in some sense, a wrong direction, then I'll go this way, and then here. So 3 steps. So you had 2 choices at 0, 0. Essentially, you didn't know, like you could have picked any one of them. And you don't have a better, any extra information to pick, like to see which one to pick. I mean, you could say, okay, because this is 800, at 300, 0, 300, its objective value is better than at 0, 200, so you should probably go there. But that reasoning also kind of fails sometimes. Okay, it doesn't mean that that part will be shorter. Okay, so this is one kind of issue with simplex. Your local judgment may not be always good. Okay, and you may be going on a long path. Okay. Another issue is we assume that we have a starting vertex. But why should we have that? And to find a starting vertex is equivalent to kind of solving another LP. So here, if B is non-negative, then there is a trivial feasible point here, which is just x equals 0. Right? If I set x equals 0 and B is all non-negative coordinates, then x equals 0 is feasible. But otherwise, you have to solve this another linear program. So what this linear program is doing is, it is adding a slack variable to all the constraints and forcing the slack variable to be non-negative and then minimizing the slack variable. What is the optimal value of this new LP if there was an x such that ax less than or equals b? How much minimum can you push S if there was an x such that ax less than or equals b? So suppose I put that particular x here, then what can I set S to, the minimum value of S, such that it is also non-negative? and the constraint remains satisfied. Sorry? BI. So I'm saying that, so is the point clear? So suppose there is some x hat, suppose there is some x hat such that ax hat is less than or equals b. Then if suppose I set here x equals x hat, what should I set s to so that the value of s is minimized and the constraint remain tight? Zero, right? Because if I set s to 0, the constraint will still remain tight because this is exactly, if s is 0, this is just saying ax less than or equals b. And I cannot set s to below 0 because of this constraint. What is an obvious feasible point of this LP? So now I don't have x, say, I don't have this. I don't know this. And I want to find a feasible point. So I should not go in recursion, that's what I'm trying to say. To solve the first LP, we said that we need a feasible point, a feasible vertex. To compute a feasible vertex, we wrote this new LP. Now if I have to write another LP to compute a feasible point here, then we are going in recursion. So there should be an obvious feasible point in this LP. I'm not saying vertex, any feasible point. Is there a feasible point where I set x equals 0, all x coordinates to 0? So let's say x equals 0. So this kind of goes away, right? This is just 0. So you just remain with, what is the solution of this? So you're just saying that S should be at least minus bi for all I. Right? And that is just saying that S is, or max minus bi. I don't need the mod. So this LP has an obvious feasible point, and from a feasible point you can compute a feasible vertex. It's not difficult. You start moving in the direction of the objective function, you will hit a face, then from there you start moving on the object. Again, you do the same, you will hit a smaller dimensional face, and so on. You will compute a vertex. So you get a feasible point, from there you can compute a vertex, apply simplex on this, and you will find an optimum solution of this. Okay, so then if this original thing was feasible, then you know that LP should stop at a point where S is 0. Right? Because you cannot set S to below 0. And when you have a point, feasible point where S is 0, that should be optimum, because you want to minimize S. Okay, so if you try to solve, so this kind of completes the description of simplex algorithm. You know how to compute the starting point, and then after that you know how to move from there, right? Now, as we kind of briefly noted, that naive implementation of simplex can be inefficient. Okay, you may not be going on the smallest path. in fact, you could take exponentially long path while the solution is just a neighbor. Okay? Suppose you have this box. Okay? And this is where you start at the bottom. And this top corner is the solution. Okay? So this direction is the cost direction, upwards. Okay? Now I shrink, make this box a little, like I push it like that. Okay? Then, so I'm pushing this side also. Then from here I could see that, oh, this is also a improving direction, so I go there. Then from here, this is also improving. Improving, 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 improving. So instead of taking one step, I took 8 steps, 7 steps. Okay, so if this direction is improving direction, then this vertex is also improving vertex. This from here, this is improving from there, and so on. This is called Clementi cube actually. Okay, so in the worst case, if you don't do any smart pivoting, or actually there is no smart pivoting known where the simplex is polynomial time. So in the worst case, it could take exponential time. But in practice, it's so it is important which neighbor you choose, and but I mean very efficient simplex-based algorithms are known in practice, and simplex algorithm takes exponential in the worst case, but works extremely well in practice with many improvements over the years. And sometimes there are some other interior point method where you don't move from vertex to vertex, but you actually move inside the interior of the polytope, and for some large problems it may do better. Finding a polynomial time algorithm, worst case polynomial time algorithm was an open problem for like almost 60 years. So after the simplex came in 1940s, until 1970s it remained open. And in 1979, almost 1980, Hashian gave the first polynomial time algorithm, which we know as the ellipsoid method. And nobody implements it in practice actually, okay, because it's really bad. But it is used heavily for mathematical reasoning and in theoretical proofs. It's very powerful because it doesn't only solve linear programming, but also convex programming and many more complicated programming problems. Narendra Karmakar in 1984 gave the another polynomial time algorithm, which is interior point method, where you actually move inside in the interior of the polytope. And this is a practical algorithm for large problems. Sometimes it beats simplex. And it also gave this new method, new tool. It revolutionized the theory of interior point methods. Okay? So this is also an important method, but we are not going to cover it actually outside the scope of this course. And after this innovation, simplex was improved even more. So the two crucial points in simplex is the starting point and what neighbors to pick. Okay? So people developed better methods to do both of these steps. Now there are 3 issues that we need to handle. In some sense, we kind of talked about one of them, unboundedness. Right? It may happen that your simplex encounters an unbounded ray. Okay? And then you just say that the LP is unbounded in the direction of the cost. So there is no finite solution which is optimal. So infeasibility. So suppose you want to solve this LP, then is there any feasible point here? So x1 is at most 2, x2 is at most 1, and x1 plus x2 has to be at least 4. Are there any x1, x2 such that these 3 constraints can be satisfied? And also the x1 and x2 can not be negative. No, right? This is infeasible. So what happens when you try to solve an infeasible problem? So a priori you won't know that it is infeasible. You have to detect that. Right? So when you try to find a starting point by solving that another LP, you will detect this. Okay, what will happen is when you try to solve this LP that we talked about, the optimal, so this has a feasible point regardless of whether the original problem was feasible or not. Okay, but when you are at the optimal point, S will not be 0, it will be strictly positive. Okay, so this is how you can detect that the problem you are trying to solve is infeasible. Basically the constraints, there is no point which can satisfy all the constraints. Okay. If the problem is unbounded in the direction of the cost vector, the simplex will again detect it. Okay. Essentially it will just never update that epsilon in the next vertex subroutine when you are finally at a point from which there is an unbounded line. Okay? And it will just return null in our implementation. Okay? So that can be detected. There could be degeneracy. Can you give me an example of a polytope that you have seen for sure, I know, where at a vertex more than 3 constraints are tight or more than 3 hyperplanes meet? Anything? Egypt, it's in Egypt. Pyramid. I mean, probably that's the only thing we all have seen from Egypt, right? Not in person, but probably in pictures. So if you see the top vertex there, how many kind of these planes meeting there? 4. Right? And in general, we talked about these cones where it could have so many lines to form, and the space between every line will be a constraint. Any 2 lines, consecutive lines, right? So there could be degenerate vertex. Now suppose there is a degenerate vertex in my polytope. I just happen to be there at that degenerate vertex, and there are d plus 1 hyperplanes tied there. Out of that, I detect d of them and form my system of linear equality. Okay, to compute the directions that we talked about by taking the inverse and multiplying by -1. Now suppose I try to move in any of these directions, what will happen? So I took the first d to form, so say that these are tight here and they will be linearly independent. Okay, in pyramid any 3 of those 4 are linearly independent. You can see that. You can verify that. Okay, so there will be an inverse of that, and you will get these directions. Now when you try to see what should be an epsilon so that d plus 1th is feasible, the epsilon will turn out to be 0. Okay, so when you try to compute epsilon for d plus 1th constraint, which you thought is not tight here somehow, okay, because you didn't check all of them, then your epsilon, the algorithm will see that, okay, the upper bound on the epsilon is 0, so when it does x hat plus epsilon di, it will just return x hat. So you didn't go anywhere, you just remained there. But what you did was you removed ith constraint and introduced d plus 1th constraint. Now you again do next vertex with some other, with a new system and with new thing. What you will see is Now the ith constraint will become tight at epsilon equals 0. So what happens is you're not moving from that vertex. You're just encountering different bases for this vertex. That's it. That's called cycling. Okay, you may just cycle on that vertex. Okay, and to handle that, you can perturb the BIs a little bit, very, very tiny. It can also be lexicographic or imaginative perturbation. And then this degeneracy will disappear. It is kind of pushing the top vertex by a phase a bit. And that will generate a small phase here, kind of. Okay, and it will spread out the 4 hyperplanes that we're meeting here. Okay, or like pushing some hyperplanes a bit inside or something like that. So you can handle that also. Now, okay, so any questions?
So like the case if we push the point a little bit lower, will we still go back to the point, to that original point?
So you kind of, yeah, so you're kind of changing the polytope in some sense, right? And you may say that, okay, what if that point was the optimal point? So you kind of made it disappear, right? So what you generally do is that the perturbation is so small. So you first of all know that the vertex coordinates are rational numbers. Okay? And so this is like a 3-4 level of reasoning now. So vertex coordinates are rational numbers. And they have polynomial size. So the denominator of these rational numbers are polynomially bounded. Okay? Now, when you do the perturbation smaller than that denominator. So you do, if say h is the highest denominator, then you do the perturbation which is less than 1 over h square. Okay? Now you will be at a point which was formed because of the deformation here, one of the vertices here. So you are actually very near to the original solution, and then you will round up to 1 over h. That is one way to do it. So by perturbing, you are changing the polytope, but you are changing it by such a tiny amount that the solution will remain nearby to the original solution. And then you know that the denominator of the original solution can be at most 1 over h, but the current solution has 1 over h squared denominator. So I can round it up. These are details. Okay, so now there is I just wanted to touch upon the duality theory, which I don't think I have a time. So basically, if you have a linear program and you want to just kind of guess an upper bound on the objective value, that kind of gives you a dual. And a very strong theorem is primal equals dual. I think in the next lecture on LP, Chandra will cover this primal duality theory. Okay? And that also kind of tells you how to solve max cut min flow, why this connection between this max cut min flow and through LP. Okay.